Hi, now we are going to discuss the third module. We'll talk about some basics in the optimizations. You've seen the optimization problem before in the previous module. Now we will dig deeper into what they are actually. So you've seen this course overview. So we've discussed the objective and constraint formulations. Now we'll dig deeper into the optimization, some technical terms in the optimization itself. We'll talk about the continuity and discontinuity of functions of that objective functions. What do we discuss? Some unimodality and multimodality. I think you've seen this in the that Mount Everest example. So we have like one that Mount Everest example. We see many optimum points. So that's what we call as multimodality. And if we have only like one optimum point, we call it unimodality. Related to that is then the global optimum point and then the local optimum, which you have seen, and then counterplots. It is then symbolized perfectly by the Himalayan mountain, and then convex and concave functions. Why do they matter? It's Hessian matrix, and then necessary and sufficient conditions for convexity and the convex region. So continuity. So remember that our f is then our objective functions. Yeah. So we are now having like one variable, in this case x, as our independent variable, like it was temperature, outlet temperature of the water in the previous example. So if we now trying to make like we start at a flow rate of a, yeah, and then we calculate the objective function, it gives us this number, and then we move on to a plus delta a, for example, somewhere here, and then we have another f, and so on and so forth until this point. So for the same a, for example, here, same a, it's not very straight. So for the same a, we have two values of f. We have two values of objective functions. And from here, because this is very easy to visualize, they are these functions, they are discontinued at this point. So this is what we call like discontinuity in the objective functions. Another example is that if we have this kind of functions, we have a kick here, but if we can see that for all values of x, we have the objective function values are continuous, yeah, and then this is also a nice example. So where all of these x values, we have like a certain f objective functions, and so these two, this curve and that curve, this is then our continuous function. This is the discontinuous. Another example of discontinuous is about the steam, for example. We have a cost of the steam, so we have low pressure steam, high pressure steam, fired, and the electric arc. So we have the temperature or pressure in this case. So for a certain range of temperature, we have the same cost of low pressure steam, and then when we jump to a higher temperature or higher pressure, the cost also jumps by a certain degree. The same goes to the furnace and the electric arc. So they are not continuous in nature. Yeah. Just another example, very silly example, is if the function is f equals to 1 over x. So we can see that this function is discontinued with x approaching 0. So if x approaching 0 from the positive x, we will have the fx will then be going to infinity. If we are approaching x from minus x to 0, the fx will then be approaching minus infinity. And the first derivative of this x is minus 1 over x squared, which is also discontinuous in this case. So unimodality and multimodality, I think we have seen this. Unimodality means one maximum point. Multimodality is we have 1, 2, 3 maximum points. Yeah. In this case, if we are moving from A to B, and then for the minimum points, we have 1, 2, like a saddle here, 3. Also minimum points. So there are many minimum points. Contour plots, the same as that 2D graph that we have seen before, but it's just like more 3D. So we have two variables x1 and x2, yeah, and then we can see that this is going to be moving towards u, or going to be in this case local maximum. So we have a 90 values of f is then 90 here, and then the values of f is 200 over here, 100 over there. And this whole line or contour represents one line here, represents the same value throughout the line. So if it is 50, that means also 50 here, and 50 there, and 50 here. Yeah, the same goes as in this case. So we have one line is then one value of x, one value of objective function fx. We could also have like a discontinuous contour. For example, this then the one value of f, yeah, and it jumps to another value of f, and then jumps to another value of f. So we have discontinuous contour, and this is one like we call like a saddle point, where you can see the projections on this plane. So we have here, we can drop down to here, it goes up here. This is like a saddle point. So convex functions, convex is if we draw a line between the, so this is then the objective function fx. So we have the variable, independent variable of x. So if we draw a line from xa to xb, if we draw a line over here, so this line, if all of these lines, the value of the objective functions is, sorry, if the value of these lines is always higher than the value of the objective functions within this range, this is what we call as convex functions. Yeah, we express this mathematically by this. So if the value of f objective functions in this region is always lower than the value of the straight line, yeah. So if we see this, so delta in this case is then 0 to 1. So 0 means it will be to x1. So sorry, 0 means it will be to xb, and then 1 will then be to xa. So any value on the straight lines over here, if it's higher than the objective functions, I mean we have a convex. This is how we show it mathematically. Another function is then the concave function. So it's the other way around. If all values of the straight line is always lower than the value of the objective functions, that we call this the concave. And we have another example. So you know this one for convex, you know that one for concave. If we have also like three lines making connections like this, 1 line, 2 line, 3 line. So we could say this also a convex function, because if we draw one line from here to there, so all the values of the objective function lies below this straight line. This is what we call as convex functions. So what happens if we draw a straight line, some of the functions goes below, some of the function goes above it. We call that like non-convex function. For example, in this case, if we draw a straight line from xa to xb, for example, so this objective functions, this area is concave. Yeah, this area is concave, and this area is convex. So we don't call it non-concave. What we call this part by consensus is non-convex functions. So we have a convex and we have non-convex functions. The problem with this convex function, I think you can see it, if you want to find an optimum objective functions, say for example you want to find the maximum value of fx, and we start from here, yeah, xa. So the algorithm will then ask us to go into this area, to this line, to this point. Yeah. So once it is on this point, it will say to us, well, we have the an optimum f, right? Because if the algorithm continues, it will move from xa to the optimum point, and then we'll move down from here, and then the algorithm will say, yeah, because the algorithm is a blind person, so it doesn't know. So the only thing that he knows is that we are now descending from our optimum point. So it will then stop and it says to us that we are already at an optimum value. Yeah, while we know that this is not the global optimum. This is only like a local optimum, while the global optimum is over here. So if we start from xb, we'll find the global optimum. But if we start from xa, we'll find only the local optimum. The same goes with the minimization. If we want to minimize this fx, so depending where we are, so if we are somewhere here, for example, it will then tell us to go to xa rather than going into this area, to this point, yeah, because if it goes to towards xb, the value of the objective function will increase. But if it goes towards xa, the value of the objective function will decrease. So it will send us to xa where we have the minimum value. If we start our search is in here, so indeed we'll go to the minimum, or global minimum value. So this is then the problem that we will encounter very often in non-convex functions. In this simple example, we can draw the objective functions. Yeah, we have only like one variable, and then we can easily draw the objective function. But imagine that we have like two variables. In the two variables x1 and x2, we can have like a 3D. But in more than two variables, like three variables, x1, x2, x3, or even more, it's impossible for us to draw the objective functions. Hence, we will not be able to see whether one solution is a local maximum or local minimum, and all the other solution is then global maximum or global minimum. You can see in these convex functions, there is always one minimum point. The same goes with the concave function. There is always one maximum point. Yeah? So that is the big difference between the convex and non-convex, convex or concave, and the non-convex. So in the convex function, there is always a guarantee that we will find the global objective function, the global solutions. But in non-convex problem, there is no guarantee that we will be able to say that we are in the global optimum point. That is then the importance of this convex and concave functions. So convex region, so the same definition applies. So you can draw a straight line from one point to the other point, like this one, and all of these points are within the region. That means these are convex, like that one and this B. But if we, in this case, the C, this part is the non-convex part. So this region, yeah, these values of x1 and x2 in this case is outside of the feasible region. Hence, this objective function or this problem is non-convex. So now take, for example, our simple case of fx equals to x squared. So if we plot them, yeah, by varying the value of x, variable x, we know that at x equals to 0, the functions is then at the minimum, which is 0 as well. And the curve looks like this, u, big U. And let's examine this a little bit further. So if we are now here, yeah, we start our search from here, so from this x1, and then we want to find the minimum value of objective function. We're not going to go that way. Instead, we are going to go this way. All right. So say that we have one step. Yeah. So this is then another x2. So x1, x2, and then the distance between them is then the delta x. So delta x is our step. How big is the step? And then we are moving in these positive directions. Yeah, not that one, not that negative direction. So we are moving in the positive direction. So then the directions. So if you can still remember this Himalaya mountain, we are the blind person. What we know is only this: how big is the step and where to move. So we are moving into these positive directions, and then moving into the positive directions, and so on and so forth. Yeah. So you can see this delta f is going to be positive, and this delta x is going to be positive. So we have like a positive gradient in this case. So below, if with x is negative, the gradient is positive. The same goes with the x is then positive, so the gradient is also like a positive. So we can see here. So we have like here the gradient is the negative, here the gradient is then positive. So you can see it here. So we have like the first derivative, which is then the gradient. Depending on the value of x, it can become negative in this case, it can become positive in this case. So if we take the value here, so we have, for example, this is minus 5, for example, minus 5. And then this is minus 4. The distance is then minus 4 minus 5 is then 1. And this value is, for example, it's a positive, right? So for example, take this value is like 4, and this value is then 5. 4 minus 5 is then minus 1. Minus 1 divided by 1 is then minus. So this area is then the minus area, minus gradient, as we can see it here. And that area is the other way around, is the positive area, as we can see it here. So that is then the first derivative of that. And since we know that this fx is at minimum at the 0 value, and this 0 value corresponds to this 0 value. Yeah. So you can see at the first derivative of fx equals to 0, that is then our what we call like stationary point, where we changed from the negative gradient to the positive gradient, like in this case, or moving from here to there, where it changed the directions. So now you can see the necessary conditions. We define necessary conditions for a functions to have an optimum point. Yeah, to have an optimum point. We don't know yet whether it is maximum or minimum, but in order for us to be able to say that a functions have an optimum point, we will have to calculate the first derivative in this case, and then where if the first derivative equals to 0, like in this point, we'll have the optimum point. Yeah, so this is what we call as necessary conditions of optimality. And but how do we know if this is then minimum in this case or maximum as in the convex? So now if we derive this further, yeah, so the second derivative of the function, or the next derivative of these functions will be 2. Yeah, 2 is always positive. Yeah, it's always positive regardless of the x values. The second derivative is always 2. It's always positive. So we know that this is positive, and we know that this is then the minimum. It corresponds to the minimum value. So we could say the sufficient conditions for a function to say that we have a minimum point is that the second derivative is positive. Yeah. And the other way around, if the second derivative is negative, we would then have a concave functions, which is then the maximum point. So I repeat again. So to be able to say that a function has an optimum point, we have to then be able to derive the first derivative is to equals to 0. Then we have the stationary point. Then we know that this function has an optimum point, but it is not sufficient to say that it is maximum or minimum. So the next check is then we derive it once again, the second derivative. If the second derivative is positive, that means we have a minimum point. If the second derivative is negative, we have the maximum point. So now we have these functions. I think you can try to find the first derivative and the second derivative to make sure to calculate either this function is convex, concave, or indefinite. Yeah, strictly convex and strictly concave. You can see it here. So equals to 0. You put convex but not strict. Without equality, it's a strictly convex function. Yeah, for practical applications in chemical engineering, this is not so much of importance, so I will just skip this explanation. So you can see, so we have the function of 3x2 square, and then the if we derive this into its first derivative, x6x, right? So we have this is then the necessary conditions where where the first derivative equals to 0, and then the sufficient condition is then where the we derive it once again into 6. 2x, if we plot them, so we have 2x lines over here, and then the first derivative is x equals to 2, second derivative is then 0. So there's nothing here, though. There is no, since the second derivative is not equals to 0, so there is no optimum point. As you can see, there's no optimum point. So depending on the x, it can be minus infinity or plus infinity. So the same goes to the concave function. So we have the maximum point at 0. Yeah, if we put this first derivative equals to 0, and then we have x equals to 0, so that x equals to 0 is then our optimum point. And if we derive it once again, it is minus 10, so it's always negative, so this would then be the maximum point. There's the conditions, sufficient conditions. How about this one? This one looks like this. So we have a functions of the blue line is then the functions, so it touches the 0 line in several locations. The first derivative, the orange one, is looking like this. So if we put that equals to 0, so we have like two values that makes this equals to 0. Yeah. So in this case, if we say it like this, we have two values that makes it optimum point, and then if we derive it once again as the second derivative, because we would like to know either they are the maximum point or they are the minimum point. If we derive it once again, so this function is neither positive nor negative. It depends on how much is the x value. Yeah. So so you can see this. So in this area, x value, the second derivative is positive, and that means it will have like I don't know. In this case, it doesn't show. If you look at this blue line, it doesn't show that it has like a maximum or minimum value, and we know that in this case, so depending on the x value, the second derivative can be positive or can be negative in this case. So we cannot use, we cannot apply that rule to these specific functions. Hence, we don't know for sure if this function has a minimum or maximum point, or if it has a minimum point, as you can see it here. Yeah. So far we have discussed only one variable. Now how about if we have more than one variable, like multivariable? In this case, we can use the Hessian matrix to represent our second derivative. Yeah. First derivative is easy, so we can just derive it. We can just derive the function once to x1 or x2, and then we have like if we have two variables and we derive it into x1 and we derive it into x2, so we have two first derivative functions, two functions of the first derivative. And then if we if we want to make like a second derivative, so we can just use these Hessian functions. So we have the derivative of f to x1 and then x1 again. So and then the next part is then the derivative of f to x1 and then to x2, and so on until derivative of f to x1 and then xn in this case. Yeah, and then in the second row, it's all about x2, so derivative of f to x2, and then we derive it to x1, and then this f df dx2 and dx2, and so on. And then here we have df dxn dx1 and df dxn dx2, and so on until df dxn dxn. Yeah, it is always symmetric. Yeah, because of this rule, because you can see it now. The necessary and sufficient conditions for the multivariable function is more or less the same like in the single variable. So if the diagonal, if the second derivative, which is then in this case the Hessian derivative, the Hessian matrix is all positive, yeah, if the diagonal element is positive, and then fx is then convex, and then if it's negative, it's in the idea around concave, yeah. If it's neither of these two, that means this is not we cannot say that this function is either convex or concave. Now these are the examples, so you can just try to apply these two methods. So see if you have you derive it into the Hessian matrix, and see if the diagonals are all positive, and you can say that this is then the convex, or if the diagonal is all negative, and then the function is then concave. Yeah. So for example, this line, the first function, this is like a plane. Yeah. There is no second derivative here, so it's a plane. But in this case, we have a minimum. Yeah. If you apply this Hessian matrix and then try to confirm that, see if you have like it should have like a minimum point. The same goes here. So it has a maximum point. So if you apply the second derivative, and then you can then see or convince yourself that it has a maximum point. How about this one? It's also the same case. This we have a saddle. Yeah, you can check it in your Hessian matrix. I think this sums up our module today. So I'll see you next time.